Stream going here. See if there's any last minute additions, and I'm going to get the screen sharing going as well because I got to show you guys the end result of Tuesday. I'll be able to tell when you can see it. This is Tuesday night at Lisa's house. So as I told you shamelessly, Tuesday was my birthday, and I got to open presents with my family. And lo and behold, my son Huey there gave me a Tom Nook stuffy that I never knew I wanted. So there we are with the aforementioned stuffy, and I believe that was the last time I've seen it because he promptly claimed it, slept with it that night, took it to school, and I'm probably never going to see it again, but that's just as well. For those of you who don't yet have children, by the way, what we used to call stuffed animals, they're called stuffies. This is just a universally accepted term. So this is a stuffy. This is Tom Nook, of course, from Animal Crossing, his favorite game. He plays that as well as Minecraft right now. So Tom Nook, that's mine. You heard it here first. All right, and another announcement, Jordan. Do you want to tell everybody what you told me a few minutes ago?
Sure. So I already told some people in classes I had with them today, but for today only, and I promise I am not in any way an ambassador for this group, but I saw a good deal and I want to share a good deal. Masterclass does a bunch of videos from professionals and celebrities in different things like writing, photography, cooking. So they have like tons and tons of different videos for today only. 1 year membership for $1 for students, typically $180. So I'll throw that in the link. And like I said, I promise I'm not getting any type of kickback on this. I just saw a good deal and wanted to share it. And we all could use a good deal whenever we can. So figured I would share that.
Thank you. And even if you are getting a kickback, that is a good deal. $1 for a masterclass membership. That way we can all gain some new hobbies with our extra time in quarantine because you can only watch so much Netflix
Yeah,
before your
just make
brain
sure make
melts.
sure make sure you put it in your calendar for 1 year before it auto renews for 180. So
Yes.
that'll be the one stipulation, is that you want to make sure that you remember to cancel it at the end.
Yes, a lot of services get you that way. They take your credit card and then you're on the hook for the rest of your life unless you manage to actually call them and cancel the service. So, very good. All right, but speaking of master class, we're trying to become masters of latent trait models. Do you like that segue? Is that pretty good? Like, yeah, I try. We started talking about this stuff last time. Tell me what you remember. You can use letters, words, gestures. I'm watching the chat window for those of you who prefer to talk that way. Otherwise, you can unmute yourself. What do you remember? CFA is a linear regression with an unobserved predictor. Yes, the latent variable is a predictor in a regression model. And it's a linear regression model because we have a linear slope relating the latent trait, the predictor, to the outcome. And in this class, what's that slope called? See, this is the audience participation portion of the program. Factor loading, yeah. What's the symbol for it? Lambda, yes. That's a slope. A 1 unit change in x gives you a lambda change in y. The rules have not changed, but we're changing notation a bit. Yeah. So lambda is our index of what? What item characteristic does lambda map onto? Discrimination, yes. The other part of the regression model that concerns the item, the intercept, that thing. That is just like an intercept in any regression model, the expected outcome when your predictors are zero. It gets what as its symbol in this class? Yeah, I'll take gestures. You can draw it, that's fine. Or you can type it. It's in front of you guys. This is a softball. I know you can do it. Mu, yeah. The U looking thing. And I say in this class because notation changes across authors and across sources. I will try to stay internally consistent as much as possible, but this is probably mapping onto more common notation than not. And E, of course, that's our error or our residual, how far off from the predicted value. We don't care what E is for each item or person, but we do care what the E variance is across people for each item. So each item will get its own intercept, its own factor loading lambda slope thingy, and its own error variance. And those three types of parameters form what is known as the measurement model. The rest of the model, the F here, let me move my giant mouse over, that stands for factor. In your textbook, it is squiggle 1, whatever Greek letter that is. I've named them squiggle 1 and squiggle 2 because I've never learned them. There's one that has a curly Q thing at the top, and there's another letter that has two curly Q things at the top, and that's how you can tell them apart. But squiggle 1 is what he uses, I believe. I'm going to call it an F. We don't need to know what F is for each subject. All we need to know is F's mean, its variance, and if there's more than one F in the model, its covariance with the other F's. And those are sufficient statistics under the assumption that the F's share a multivariate normal distribution. So even though the individual item equation has this idea of F for each person is not a model parameter. Said differently, F is a random effect. So for those of you who've had multi-level, we used to have random intercepts and slopes that were given by U as a notation. This is F. It's the exact same thing, just a different letter because it's a different context. Random effects are latent variables. So what is this model trying to do? Let's go big picture before we get into the details. What's the point? Why would you fit a model like this to data? What research question would you be answering? And by the way, if you're shy and don't want to have a silly answer, you can type to me just me in the chat window where only I can see your answer. If that helps you guys be a little more willing to type. How well an indicator represents a latent trait? Yes, that might be one reason we'd fit a model, is to operationally define how good an item is. That's one. Another answer, the factor structure. Yeah, more generally, dimensionality. So if I only have one dimension in my model, meaning that I think that all of the items that I'm analyzing are supposed to measure one trait, I'm going to get estimates and standard errors for the loadings. That's going to answer the research question as to whether or not an item actually is related to the trait. But more generally, what am I trying to capture? What am I trying to mimic? What am I trying to approximate? What characteristic of the data am I trying to get back to with this factor model? No answers? Okay, so maybe we gotta go back over this again. Yeah, covariance question mark? Yes, covariance. It sounds weird, but it's true. The point of fitting this model, even though it's phrased in this way of trying to predict each individual score, what we're actually trying to do is to create a predicted pattern of covariance across the items that matches the real one from the data. That's what this is trying to do. So we don't actually care what F is. F is an idea. This isn't a predictive model in the same way that you're used to thinking of it in a regression model where the goal is to explain why some people have higher responses than others. What we're trying to explain is the dimensionality of the responses, but we still don't know why each person has a different F. So this is kind of an intermediate step between answering research questions that would concern relationships between variables. So in our model, clicking through, this is slide 10 here, the models are often described using these sorts of path diagram pictures where real information you have in your data set is given in rectangles or squares, and variables that are defined as part of your model that are not real, that are latent, are in circles. So that includes the factors in this case as the predictors, as well as the error terms that go with each of the items. The role of the model is to try and figure out how much of the variability in each item response is due to the factor. That part is a function of the slope for each factor, the factor loading that goes on the paths here, and then how much of it is error, which is just not the factor. So that demarcation of how much is truth, so to speak, versus error is what this model is designed to tell us. And the way that we know that it's right is if this model can anticipate what the pattern of covariance is across the items. So question, what is a good amount of error? That would be a subjective decision, but generally speaking, the factor loadings, when they're tested for significance, like that's a really low bar. Like you can have a significant factor loading that's only 0.1. And that would mean that if you put it into a correlation metric for a standardized loading, let's say 0.1, that there's a 0.1 correlation between the item and the factor, that could be deemed significant, but that's not good enough. Because if you take a 0.1 correlation and think of it in terms of an R square, 0.1 squared would be 1% due to the factor, 99% due to the error. Um, I would say I would like to see factor loadings that are standardized above 0.5 before I start to have some kind of faith in what I'm doing. Um, we'll talk more about how the strength of the factor loadings contributes to assessments of how good the model is in unexpected ways. But just to put a pin in that for now, the less reliable your measurement, so the lower the factor loadings, the easier it is to look like your model fits well. It's actually a bad thing from the perspective of reliability as well as from the perspective of having a good indication as to whether you have good fit. So more is better. There are cutoffs for significance, but those are not as useful and as thinking of these as effect sizes. The other part of this has to do with the interpretation of what error means. You will also hear error described as unique variance or specific variance or residual variance. All of those terms mean the same thing, but they have different connotations. So when you think of error, like unique variance sort of means like there's still something there, it's just unique to that indicator and we don't know what it is. It's not error, it's just unique. Like that sounds really positive, right? Like that's a nice spin to it. The same way with specific variance, right? It's not general, it's specific. It's all the same thing. I'm going to date myself, but there used to be a show. I'm trying to remember how old it is. I want to say it's from the 90s, and it was called Dinosaurs, and it was this weird, like, people in costumes. It wasn't animated, but it was like a dinosaur family. Okay, Megan remembers. Thank you. Does anyone else remember this show or have heard of it before? Okay, I'll send you a YouTube link here if I can remember to. But there was a baby dinosaur, and he used to say mama and not the mama. He called his dad, not the mama. And so every scene, like he'd yell at him, like, not the mama, and like hit him with a spatula. So that always reminds me of factor analysis because what I have here is factor and not the factor. I don't know what error is. It's not the factor. That's what I know. It could be something that you're measuring that you care about, and if you had more items that were like it, you could tease that apart. It could just be random noise and you have no idea what it is. It's not the factor. Now, if you have enough information to try and pull apart different reasons for not the factor, you can do that by adding factors. So for instance, if some of your items come from self-report data and some of your items come from other report data, Like you ask a child's teacher or a child's parent, or you have a person and you ask their partner questions about them. Well, you can probably separate out how much of what your measurement is, what are the questions about, versus who is answering the question. So, what would be considered not the factor in that example of dyadic data would be a combination of who answered the question and error. Well, if you have more than one question from each source, you can pull apart that who answered the question and put it in as another trait in your model. That's known more generally as a method factor. So there's lots of choices that you get to make to try and split apart reasons for error that would be interpretable in some fashion. But just know that this model is agnostic. It's factor and not the factor. That's what this says right now. And Dinosaurs was a funny show. At least I thought it was when I was like 10 or whenever the hell it was on. So I'll get back to you on that one. See, I promised you, I think, at the beginning of the semester, I'd give you some pop culture references for the older generation. I don't know what letter I am. I think I'm Gen Y, maybe? I don't know. Am I Gen X? I don't know. Anyway, question. So, would any variable about respondent characteristics have method factors like race or gender? Potentially, but you wouldn't necessarily be able to tease them apart. So if you gave a survey to a person and they answered all of the questions about themselves, then you have confounded your measurement because there's only one source of variability. So there's no way to pull apart how much of the error variability is because of the person. If you had more than one source, you have a chance at being able to operationalize how much variability is because of the source. You'd have to have more than one, though, and it'd have to be consistent across the different factors. Likewise, if you had a two-factor model and you have trait A, and trait A is measured by questions that you answer, and you have trait B, and trait B is measured by questions that your partner answers, you are screwed because then trait and method are confounded. You'd have to have each person answer questions about trait A and each person answer questions about trait B to be able to have enough unique information to pull apart how much of the variability is due to who answered versus what they were answering about. That type of model, by the way, is called a multi-trait, multi-method model, where you try to operationalize the different factors as the traits and the different sources of respondent covariability as the methods. I have been systematically adding the Brown textbook. So it's sitting right here, actually. This your course textbook that's available at the library. I've been downloading chapters and uploading them into Icon for you. So I also added chapter 6, which is multi-trait, multi-method, even though I didn't assign that as a reading, just so there you have it. Okay, so we're in the business of predicting covariances. To the extent that our model anticipates what the covariances are in the data, we have some kind of faith in the dimensionality that our model presupposes. That's the game that we're playing here. The way that the covariances are predicted is fairly straightforward, even though the math gets a little hairy. What a model like this says, so I'm on slide 10 of lecture 4, is that the only reason why the items y1, 2, and 3 were correlated is because they all measure F1. And once you take that into account, once you factor out F1, as it were, what's left, the not the factor parts of each of these items, is unrelated. This is known as local independence, the idea that the errors are unrelated. The variables themselves are related to each other, but you're saying that relationship is entirely captured, attributable by, predicted by this factor. Likewise, these other three items are only related because they measure this factor. And once you control for that, the errors are unrelated, local independence. This model also says that the only reason that, say, item 1 is correlated with item 6 is because the traits they measure are correlated. And so then the predicted relationship goes through the loading, through the covariance, through the other loading, and gets over here. So these are all very specific patterns where your model is going to try and estimate the most likely value for these loadings And the job of the loadings is to try to reproduce these covariances. And at the end of the day, you're going to get, okay, what does my model say the covariances look like? What are they in the data? And how well do they match? So questions. How is that different from the uncorrelated errors assumption of alpha? It is not. So alpha, in this case, if I were to try and apply that language here, to have alpha be a valid measure of some score reliability, let's say for these three items, would mean that these three items all measure one thing. The errors of these items are unrelated. But here's the tricky part. There's one more thing that it takes to have a valid alpha. Do you remember what it is? Local independence, uncorrelated errors, unidimensionality. There's one more. Number of items is what makes alpha higher. But what's the assumption across the items? Equal discrimination, yeah. So lambda, our loadings here, those are our indices of item discrimination. They have to be equal for alpha to be valid. You know what? That is a testable hypothesis. I can tell M plus, hey, can you make those three numbers all become the same value? And you can see if that makes the model fit worse than having an alternative in which they each get to be whatever they want. So whether or not the assumptions hold of alpha becomes a readily testable process. The role of this process is to verify those assumptions. And what we will get to as an alternative measure of reliability that does not assume that these loadings are the same and that the errors are unrelated is omega, because the loadings go into the formula and so do the error covariances if you have any. All right. Does it make any sense to have an alpha for all 6 items? This is an easy one. I can watch your faces. Does it make any sense to have an alpha for all 6 items if this is the underlying structure? Yeah, no. Alpha only makes sense for unidimensional things. You can't measure how reliable 2 things are at the same time with one number. Doesn't make sense. Same thing with omega. Okay, questions? Are you guys with me? All right. So the hairy part, how do those covariances actually get predicted? We need some notation. So this is about where we left off last time. I'm trying to get to slide 15. This is what it looks like. So sigma is what the model says our covariance matrix across items is supposed to look like, where on the diagonal is the total variance of each of our items, indicators, same thing, and on the off diagonal is the covariance. So this is the supposed to, the predicted. It's saying that that comes about from 2 places. The red and blue here, that's the factor model. So the red, the lambda, that corresponds to what the combination of zeros or not zero elements were in the previous equations. So that picture says the first 3 items measure factor 1. They do not measure factor 2, so they get zeros. Can you all see my giant pink mouse? Okay, good. Likewise, the second 3 items do not measure factor 1. They do measure factor 2. Sandwiched in between here is the variance of factor 1 in the first place here. In row 2, column 2 is the variance of factor 2 and the covariance between them. We have to square the loadings to get to that combination. So the proportion of variability in an item that's due to the factor is the loading squared times the factor variance. So to have this lambda matrix this way and then it's transposed this way makes that squaring happen. So whenever you see this kind of format, something and then something transpose around it, that's squared in matrix world. So this gives you the lambda squared times the variance of the factor, or the covariance if you're talking about covariance between factors if you're talking about items that don't go on the same factor. And then the last part of this is this what's known as a diagonal matrix, where we have the residual variance for each of the indicators or error variance, not the factor variance. And these zeros in the off diagonals correspond to the lack of correlations by directed arrows in the picture. So this latter psi matrix here is saying the errors are unrelated. The only reason why these items were correlated is up here in this lambda matrix. And what is this one? Can anyone help me out? What's the blue one called? I'm blanking on it. Theta? It could be. I don't remember. Phi? Phi. Okay. Yeah, phi sounds right to me. I know this purple one is psi because I used to lead Psi-Chi. When I was a faculty member in the psych department, I did Psi-Chi, and so I know that one. But yeah, this one, phi. Yeah, that one. Factor variances and covariances. There we go. For those of you who've been through multi-level modeling, this set of equations should look really familiar, because what we're calling factor variances and covariances was the G matrix of random effect variances and covariances in that class, and what we're calling the item error variances down here was the R matrix. So if this is looking familiar, it is familiar because we are secretly learning multi-level modeling this semester. Okay, so if I break that down into what that says about each element, so this is what sigma looks like when I work through the math. The variance of each item is partially due to the factor and partially due to the error left over, where the amount that's due to the factor is weighted by the loading squared. So I've got loading squared times factor plus error, all going on the diagonal of this thing. The items within the same factor, their covariance is directly predicted by their loadings and the variance of the factor. So the same is true for factor 1 and for factor 2. And then if you go to the off diagonal, so this pattern of like chunk and then chunk like that, that's called block diagonal. If I go to the off block here, this section, this shows how the model predicts item covariances for items on two different factors. It's the loadings and then the factor covariance. That's what you need. The factor variances actually drop out if you work through the math. So this is a very strict set of predictions that tells you, using the factor loadings and using the factor variances and covariances, what the core covariances between the items are supposed to be. So this is my predicted matrix, and we're going to compare that to the real one, which is going to be called a giant S. All right. How are we doing? Who likes matrices? Not me. Anybody? Looking for yellow thumbs? Nobody. No, nobody's willing to admit it. If you like matrices, that's okay. I'm just one of those people who doesn't, I don't think that way. Like it's like thinking in another language for me. But I wanted you to see it. So take home message, the factor loadings and the factor covariance give you a model implied version of how the items are supposed to be related to each other. We compare that predicted version to the real one and we see if we're right. Okay? That sound good? Okay. All right. So how do we do this? So has anyone thought to themselves at this point, like, what? Like, we're having these imaginary variables, and these imaginary variables are going to have a covariance? Like, what the hell voodoo is that? Anyone thinking along those lines? Because I totally was. Question. Yes, thank you, Kelly. Because, yeah, it's like these things are imaginary. How are they going to have a variance? Is that like the number I that's like not a real number or something? I'm trying to remember math from high school. It was a very long time ago. Question, is it important that you understand the matrices? Not really. If you're not familiar with matrix addition and multiplication, I can live with that. The programs will do it for you. I just wanted to show how the model actually creates that predicted matrix. What it ends up being is something that you'll get in your output, as well as all of the measures of discrepancy. So no, it's not mission critical. But yeah, how do we get numbers out of imaginary variables? So this next section is all about that. And it's a process known as model identification, which means two things. It means giving the pretend latent variables that are our predictors a scale, and it means making sure that this system of equations is solvable mathematically, that it's possible to even do this. So it means two things. All right, so scale is necessary and not sufficient. And what do I mean by scale? We're assuming that all of our factors have a multivariate normal distribution. That means that each factor needs a mean and it needs a variance. And if there's more than one, then it needs a covariance. And we can choose whether to have that estimated or be zero. So covariance needs to be accounted for. The second part is more complicated, and that's to make sure that it is solvable, because this is a complex system of equations that you have to have enough pieces of information going in to solve. So item means, that's the data going in that allow the items to have their own intercepts, usually a one-to-one match, so there's no problems there. Likewise, the items have an original variability that come from the data, and that is going to be perfectly reproduced by the item error variances for the model. They're going to plug whatever hole the factor leaves behind. So not the factor plus the factor gets you back to the original, no problem. It's the covariances. That's where the problems can come in. It's making sure that you have enough data going in to identify all of those factor loadings that are supposed to be creating the covariances. And so that's the part that gets a little bit tricky. We want to make sure that we have at least as many covariances as we have loadings that are supposed to be creating them. Okay, so questions before I jump into this? Okay, most of you are not on camera, but those of you who are on camera don't look very excited right now. Is it just because it's 2:30 in the afternoon? Is that the problem? Is there anything I can do to make it more exciting? No, I'm going to put on a show in just a minute. I have a bit that involves singing, for better or worse, because it's germane to the topic, I swear. Yes. Okay, sarcasm. Everyone is excited. Yeah, I know. It's not exciting, but think of all the employment opportunities that will be afforded to you when you learn how to do this shit. That is exciting. Being paid is exciting. Question, why did the covariance must have a ratio bigger than 1? Because otherwise it's not mathematically solvable. You need to have at least as many covariances as you have loadings going into your model. So that's what we're going to talk about next. Okay, so creating a scale, that's part one. Basically, something got to be 0, something got to be 1. That's the easy version of this. There are two primary ways in which a factor that is a pretend imaginary thing gets a mean and gets a variance. The easiest way, and the way that I'm going to ask you to use to start out this process, is to pretend that the factor is like a z-score. So we're just going to say that it has a variance of 1, just like a z-score does. Problem solved. Variance of 1. If we do that, each of the loadings for the items that belong to that factor can then be estimated, and they can be whatever they want. The term for that is a congeneric factor model. You may read that, congeneric. That means each item gets to have its own loading. If each item loads only on one factor, that is a simple structure model. So if you set the factor variance to some known value, you can then estimate all the loadings. It works. Typically, that factor variance is estimated at 1, but it doesn't really matter. The downside of this approach is that if your factor is to become an outcome of other things, you can't have its variance fixed to a constant, because its variance has to be able to adapt to become variance left over after it's predicted by other stuff. So that's the one drawback to this approach, is that it works really well in preliminary analyses When you're trying to just nail down what your factor structure is and you're looking at sort of one factor at a time or maybe two factors at a time, when you get to a larger, more involved model where your factors can be downstream of other things, then estimating the factor variance is going to become necessary. But then that changes the scaling. The other way to give your imaginary variable a variance is what's known in your textbook as the marker item method. And this means that you just arbitrarily pick one of your items and you say your factor loading is 1 and the others get to be estimated. And if you fix one of the loadings to be 1, you can then estimate the factor variance instead. So in larger models in which the factor is to become an outcome of something else, this is the way that you have to do it. This is what M plus does by default. This is what Stata does by default. I'm not sure about Lavon, but I'm guessing it follows the same convention that always the first item is in the default structure of the syntax for these programs has its loading fixed to 1. Now, what that means is harder to explain. You're not saying that the loading is perfect because this is the unstandardized solution. What you're trying to do is pass information from the item up to the factor regarding variability. You're trying to say the factor variance, whatever number that is going to be the same number as the variance in the item that is due to the factor. It's just going to borrow that number and use it as the scale. So it's harder to understand what the number means because it's tied to the metric of the item. But just as an example, if I have a standardized loading of say 0.9, so putting this onto a correlation metric, and the original item has a variance of 16, then the factor variance that would get estimated as a result of constraining this loading to 1 would be the loading squared times the variance. It would be 12.96. So of the 16, right, 12.96 is the good part, is the factor part. And so that's what goes up here in the factor variance column. The only way that this can go wrong is if you pick an item to be the marker and you give it a loading of 1 and the item has no relationship to the factor. So what we're doing is taking the part of the item's variance that's due to the factor and calling that the factor variance in this scaling approach. If that item has no variance due to the factor, if it's unrelated, then that will fail because you're passing up no variance. Okay, this is confusing, right? Something's got to be 1 and the rest of it rearranges itself. That's what ends up happening. So I promised a minute ago that I would give you a little bit of levity by singing. Okay, here it is. So speaking of birthdays, all through high school and all through college, I worked at restaurants and I was a waitress. And in college in particular, and actually my last year of high school, I worked at restaurants where we had to sing when it was people's birthdays. Anyone else have to do this? Anyone? No, you guys lucked out. Well, so I worked at a place called Grisanti's, and it was kind of like the Olive Garden, except they had loaves of bread instead of breadsticks, but it was the same premise, like all the salad and bread you can eat, and then a giant plate of pasta. And so we gave out ice cream for people's birthdays. I'm showing you carrying the ice cream. This is me mimicking this. And we stuck candles in it. And what we would have to do was go around to all the other waitresses and waiters working that day and be like, can you come sing with me? Can you come sing with me? And it gets to the point where you can see someone coming with the plate, you like run because you don't want to have to sing. But because we all eventually had to sing, like it was just good practice to show up and do the singing. So whenever I was in a situation where I was forced to sing, I would always start singing first so that I could pick the key because I have a very low singing voice. So I would always start off and the song goes, me, 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 happy birthday to you, hey, happy birthday to you, ho, happy birthday, dear so and so. And then people of the opposite gender would lean in and say, baby. Happy birthday to you. And then we'd all clap and run away. So I controlled the key of the song. Thank you. Thank you. Yes, that was not my best rendition, but I think it works for our purposes. So I controlled the key of the song so that I would be able to sing comfortably. And but what often happened is some other girl would show up and she'd be like, "Hap," and I'd be like, "Shit." Like I don't have that range, right? Ha, that's a bad place to start for me. But even if I could sing that way, I'd still know what came next because the song of happy birthday, you know what the notes are. Like they're the same distance apart. So when you play a song on an instrument or you sing, the relative distances between the notes are the same, right? You can transpose the key and the song is the same. It's exactly like that, what we're talking about here. It's like the one is like the key that the factor is in, and you just have to set that, and then everything rearranges itself relative to that anchor point. So I know that if, for instance, if I'm using the marker item method and the first item loading is given a 1, if the second item is a stronger item, its loading goes above 1. If the second item is a worse item, its loading goes under 1. And so you don't have to worry about getting this wrong. It's not that any choice is going to make the model fit or work better than another choice. It's that something's got to be one, either one of the factor loadings or the variance, and all the other parameters just rearrange themselves from that anchor point as the key. Okay, questions screaming in from all of that. Is it possible that the factor contributes all of its variance for one item? I'm not sure I understand the question, but is it that the item could perfectly measure the factor? Because that could happen. So if the item perfectly measures the factor, then all of its items variance becomes the number that is the factor variance. So it literally means like one in a standardized sense. That could happen. That's very rare, but in theory it could happen. The only way that this could go wrong is if you assign a 1 to a loading where the true loading is 0. Like if it doesn't have any true factor variance to pass up, then the model will blow up. And I have seen that happen once in practice, but that's the only way it can go wrong. So other questions. So it doesn't really matter what the variance is set at as long as we know what it is. Correct. You could say the variance is 6 and everything will just rearrange itself. It'd be like ha ha, like just rearrange itself relative to that anchor point, right? You could give it a variance of 100, whatever you want, doesn't matter. Nail it down to something. One is the common choice, but it doesn't matter. So something got to be one is your first rule of factor identification. That sets the metric for the factor's variance. Okay, with me? All right. Grateful that you didn't have to be a singing waitress at any point in your life? Yeah. I did. We also did Shoney's. Do you guys know what a Shoney's is? It's kind of like a Denny's, like an all-night diner with crappy food. Okay, that got some thumbs up. The song for that one was like happy birthday, we're so glad you came. It was like really annoying, much worse. But yeah, when I started graduate school, by the way, and I was a GTA, I actually made half as much money as I did waiting tables. That was a rough awakening. But I am here to tell you to persist because when you come out the other side, you will make more money than you would waiting tables. I can almost guarantee it, especially if you learn this stuff. Yes, Texas Roadhouse dances. I suspect that the Shoney's people did not come up with that jingle by themselves. I suspect that there was some plagiarism involved of crappy happy birthday songs. But anywho, so something got to be one. That's your first rule in setting the key of this model, so to speak. Something got to be 0 is your other rule. The easiest thing to do and the thing that is almost always done, make the factor mean 0. Problem solved. So if you continue with this idea that the factor is given the same scaling as a z-score, if its variance is 1, you make its mean 0. If you do that, then all of the individual item intercepts are estimable. No problem. So factor variance does not need an estimated mean. Factor does not need an estimated mean or variance. You fix them to 0 and 1. That way all the item parameters are estimable, excuse me. The other option, which is possible but rarely invoked, is to fix one of the item means to 0 instead, so that its mean goes up to become the factor mean. So that information is just being passed up the stream. The only situation in which I have seen that done is in the context of growth models, where you're trying to measure change across a set of observed indicators, and you want the amount of the variable to be up at the factor level and not at the indicator level. So if you fit a latent growth curve model, for instance, the indicator intercepts are all fixed to 0 so that their amount of change goes up into the factor as information for that. But otherwise, we don't tend to see it that way. So you can do it this way, but that's not what's done. So the combination of the choices looks like this. Something got to be 1, either an item loading or a factor variance. Something got to be 0, either an item intercept or the factor mean. So this corner up here is the default of most programs and the most common combination, which one of the items is given a loading of 1 so that the factor variance can be estimated, but the factor mean is still held to 0 so that each item can have its own intercept. That combination is what is typically done. There is no wrong way to do it though, because these variables, these factors don't exist. We got to nail something down so that the model parameters all line up relative to that anchor point and we're in business. So other questions. Did you say that this is the unstandardized solution because setting the mean to 0 makes me think standardized? Yes. It is the unstandardized solution that I'm talking about, even though that does sound like a standardized way to do it. Yep. In the same way that you can choose the factor variance to be 100 or 6 or 1, you can choose the factor mean to be 50 or 12 or 0. 0 is the mean and 1 is the variance is just a standard, typical, that's what I mean, not standardized, but often done strategy. But you just got to nail it down to something that is a known variable that you've known constant that you feed into the system. What is the bottom right one? This is a mess. This is the version where the metric of the factor is taken entirely from the metric of variable 1. So the factor's variance becomes the amount of variance in the variable that is due to the factor, and the factor's mean becomes the mean of item 1. So it just borrows the scale from item 1 entirely on both sides, the mean side and the variance side. I will ask you to do in assignments, like assignment 2 and 3, is this top left quadrant right here, where the factor mean is 0, the factor variance is 1, and that way you can estimate all the factor loadings because the variance is known, and you can estimate all the intercepts because the mean is known. So keep that in your head. Loadings go with factor variance, intercepts go with factor mean. I refer to these as sort of the two sides of the model, the mean side and the variance side, for a reason, because they're two separate sets of identification concerns. The pretend variable's got to have a mean and it's got to have a variance. Okay, how are we doing? Thumbs up, virtual or otherwise. Keep the questions coming. See, many of you are taking advantage of the private option. That's one of the few things I like better about this Zoom world that we're inhabiting, right? Is to be able to control the questions and the dialogues. Okay. So this is how we take pretend variables and we give them a scale. Mean and variance. With me on that? Okay. Now the second half of it, making sure that all the rest of the model parameters can actually be found relative to that anchor point. That's identification. So going into identification, we got to pay attention to both parts of the model, measurement model, which is item stuff, item means, item variances, and item factor loadings, item intercepts, item error variances, item factor loadings, there we go. Structural model, which is factor things, means, variances, and covariances. And what controls how many of those that we can have is your degrees of freedom. But wait for it, In this class, degrees of freedom has nothing to do with people. And it doesn't have to do with the number of effects either. So it's not like numerator versus denominator. No, this is a third kind of degrees of freedom. It has to do with the number of items that you have. And the formula that is used to tell you how many possible parameters your model can estimate is a function of the number of items, which is v here for variables, I guess. So v times v plus 1 over 2 plus v. That's the formula. If you have, say, 4 items, then that formula gives you 14. I can estimate 14 things and before I go bankrupt. So the more items you have, the more model parameters you can estimate. What am I estimating? These things up here: item factor loadings, item intercepts, item error variances, factor covariances, factor means. Those are all the kinds of things I need to estimate. And the number that I can have of them is constrained by the number of items. So we're going to talk about total degrees of freedom versus model degrees of freedom. The idea of, given the information that you have in the data, how many model parameters can that give you? And you got to have more in the data than what you're asking for. Otherwise, you get overdrawn. Should the parentheses be 4 instead of 5? It's quite possible. Yes, thank you. I did the math instead, so fix this, please. This is 4 plus 1, which is 5. Yes, thank you for catching that, guys. I appreciate it. Divided by 2 plus 4, though. I'm pretty sure that part is right. So I'll fix this and repost the slides. But yeah, that's a 4 in there. Thank you. So there are rules about this, and the rules are very complicated. But I can break it down for you in a much easier way. It all boils down to covariances versus loadings. That's what you got. So here's what it looks like. Let's say that I've got 2 items. I think that 2 items measure 1 factor. Okay, so let's count the number of things that would have to be estimated here. In all of these slides, I have 2 columns denoting your 2 different options for setting the scale. So in the left-hand column, this corresponds to having a factor that has a set mean and a set variance. The term is fixed. So if I fix the factor mean to 0 and the factor variance to 1, I don't have to estimate either of those. But I do have to estimate 2 loadings, 2 intercepts, and 2 error variances. So that's 6 things. If I identify the model the other way, where I fix one of the loadings to 1 and one of the intercepts to 0 so that I then estimate a factor variance and a factor mean instead, it still works out to be 6. So that doesn't matter, right? So we can just look at the left-hand side here because it makes it easier. Only problem, how many pieces of information do I have going in? Yeah, neither side is worse than the other. These are 2 equivalent ways to scale the model. So long as the item that's given a loading of 1 has a relationship to the factor, it will work out. They're just 2 different keys to this to start the song in. But let's look at the total number of degrees of freedom. If I have 2 items, that's 2 times 2 plus 1 is 3, divided by 2, that is, doing the math in my head, it works out to be 5 pieces of information. That's what I've got. 2 means, 2 variances, and a covariance between the 2 items. That's easier. I can't get 6 things from 5 pieces of information. It's overdrawn. The term for this is under-identified, meaning not possible. To put this in simpler terms, it'd be like if someone gave you this equation, x plus y equals 7. Well, I could do 6 plus 1, 3 plus 4, 5 plus 2. There's an infinite number of solutions that would satisfy the same equation. There's no way to lock onto what the right answer is supposed to be. It's not solvable. In order to solve this, in order to create a model that is estimable with 2 items, I got to make some concessions. I got to make some constraints. Question, if the model is under-identified, would we get an error message in M+? Yes, you will. you will get a warning message that says, yeah, this doesn't work. And you will get estimates for things, but then they will have no standard errors, no test statistics, and no p-values. It'll be like, it blew up at this point. So yeah, you will not get results if it's under-identified. But we can identify it if we're willing to make a couple concessions. For instance, if we're willing to say that these two loadings are the same number, rather than estimating two separate loadings, I estimate one, I force them to be the same, then that solves this problem. So if you have two items that are supposed to measure a factor, you cannot do that without assuming that the items have equal discrimination. Otherwise, it's not identified. And wouldn't that mean that they're contributing both the same? Yes, it does. That's what that means. So to put this more straightforwardly, there is only one covariance between these two items. You cannot get two loadings out of one covariance. You can get one loading out of one covariance, and then you're even. So then this model would perfectly reproduce the covariance between those two items because it's only one thing. Question, is this better than the add shit up model because you still get info on variances and covariances? No, not really. If you're adding shit up, you're assuming that the reliability is perfect, whereas you would get some sort of not perfect to the extent that these standardized loadings go below 1. So I guess in that sense, it's a little bit better. But this, having only two items, does not allow you to test whether or not you actually have a factor here. You can make this work if you're willing to force the two loadings to be the same, but it doesn't actually answer your research question as to whether the items measure the same thing. You don't have enough information to say that. So it's just sort of regurgitating the covariance. The one thing that you might get out of it is just assuming, rather than having to assume perfect reliability, you would have some imperfect reliability. So the factor contains the good part, so to speak, that would go and be related to other things in your model. Okay. Let's see, 3 o'clock, not there yet. Are you guys with me? Okay, other questions. So don't do this. Okay, don't plan a study with only two items for a factor. That is very bad strategy. Next one, just identified. That's what you get if you have three items. So if I have three items, I have three means, three variances, and three covariances. That's what's going in. What has to be estimated? Well, if I fix the factor to have a mean of 0 and a variance of 1, then I've got three loadings, three intercepts, three error variances. So my three means perfectly reproduced by the three intercepts. My three total variances for the items will be perfectly reproduced by the error variances for each, because whatever is not the factor, it will just estimate that amount to plug the hole and get back to the total variance. And in this case, because there's only three, those three covariances between the items are going to be perfectly captured, perfectly reproduced by the three loadings. So there's no degrees of freedom left. You have taken the data, estimated all possible parameters for them, and what you have is a description of the data and not really a model. So you can't know if there is any evidence that these three items measure one thing, because all you've got is a reproduction of the covariance. There's no degrees of freedom left to make any testable hypotheses with. If you wanted to constrain the loadings to be equal to each other, then you could pick up 2 degrees of freedom and you would be able to have those left over to test against. But that's not often what people do. So just identified is when you're even, and it's actually not a good thing. It's the bare minimum to be able to pull this off. So 3 items, also not recommended for a factor. And in the appendix of one of the book chapters, he walks you through the algebra as to why you can do this. And so this is included just for reference because I thought it was helpful. This shows you how you can start with a correlation matrix between the items of these pairwise combinations, solve for any one of these things, and substitute in to figure out what the loadings are supposed to be. So point being, you got 3 covariances. They're perfectly recreated by the 3 loadings. So it's not a model. It's just a description of the data. 4. 4 is the magic number. Once you have 4 indicators, then you have 4 means, 4 variances, and 6 covariances. The 6 covariances is the key because if I have a one-factor model here, I only have 4 loadings. So again, the 4 means perfectly captured by the 4 intercepts. Done. The 4 indicator variances will be perfectly captured by the 4 error variances. They're just going to plug whatever hole is there to get back to the original item variance. Done. The 6 covariances, though, those are going to have to be captured by 4 loadings. And that's where your degrees of freedom come from. There's 2 left over. So the model isn't going to be perfect. How close to the real data you get is an empirical question. And if your items are measuring one trait like you think they are, then the pattern of covariance among the 6 covariances should be well approximated by putting in these 4 loadings and the covariance patterns they predict. That's the goal here. So 4 is the minimum number it takes for the model to be estimable and testable, to be able to have an answer key with which to compare it to, which is the covariance pattern in the data. It's not going to be perfectly reproduced. The question is how far off you are. All right, how are we doing? Okay, so 2 steps of this identification process. Every factor in your model needs a scale. Something got to be 0, something got to be 1. You can either set the factor mean to 0, which is almost always the case, or set an intercept to 0. And you can set a factor variance to 1 or one of the item loadings to 1. And it can be any number, but those are the most common. So then things have a scale. But just having a scale is not sufficient to ensure that all of these parameters are estimable. If you have each item getting its own intercept, its own loading, and its own error variance, you need 3 items for the model to be estimable. You need 4 items for it to be testable and estimable. So the term for this is over-identified, meaning that you've got degrees of freedom to spare. You are over the number of, you have more covariances than you have loadings. That's usually what it boils down to. So another question, if you have a larger latent trait with subcomponents, but the subcomponents are just identified, is it better to ignore the subcomponents and estimate one latent factor since they'll be just identified? So this is why this set of rules here is why in the description for your assignments, I said that each factor has to be measured by, I think at least 6 indicators is what I had said, because then you have room to be wrong, right? If you had a factor that only has 3, you're not going to be wrong no matter what you do. Where's the fun in that? So if you're in a situation where you have, say, 3 indicators of a factor, if you put more than one factor in the same model, the model as a whole will be over-identified. So do I have a picture coming up? Yeah, here's some pictures. So for instance, if I had 4 indicators of 2 factors, each of these factors is under-identified. If I just look at it in isolation, I've got 1 covariance, I can't pull 2 loadings out of that. But if I put it together, then I have 4 loadings, or 2 loadings and 2 variances, that approximate the 6 covariances across these. Now the model is over-identified because I've combined forces. So in your projects, if you have factors that only have a few items, you can test more than one factor at a time to solve this identification problem. So if the scale has 5 items, you can't test for 2 factors because one would be under-identified. You can because it's locally under-identified, but globally over. So this is tricky. In this case, this only works as a model if there is a covariance between these 2 factors. If the covariance is 0, then functionally it's like each of these has to stand alone, and it can't. Likewise, if you had 3 items that you thought would measure a factor, but it turned out you were wrong, and one of them was unrelated, then it's as if you only have 2 items and you're locally under-identified. So if you had 5 items, you can fit 2 factors. As a whole, the model will be over-identified. So if you had 3 items on one factor and 2 items on the other, because they can borrow information across the factor covariance, that will work. If the factors were not related to each other, the one that has the 2 would have a problem. The one that has the 3 would be okay. Okay, fun stuff. So yes, as a general strategy, you want to test each factor separately, because that way you have the clearest interpretation as to whether that set of items holds together in a way that is consistent with the one factor you think it should. Where that falls apart in practice is when you only have 2 or 3 items. In that case, you cannot test a factor. It's not identified. So then you would have to pool across multiple factors. So if you were in a situation where you had 2 3-item factors, that should be one model, because otherwise you can't do it. It's just going to perfectly reproduce it. One thing that's tricky about these ideas here is the level of judgment that is mistakenly applied to something like this. So I'm going back to this 3-item factor. Okay, so this is just identified, which means you can't be wrong. Now that sounds like a positive thing, right? You can't screw it up. But it's really not, because you don't have the room to show that it's only one factor instead of 2. This does not provide you with any evidence towards your dimensionality because it perfectly reproduces the data. And the other thing that is missing so far in all of this discussion is, what are those factor loadings anyway? So let's say that I have a 3-item factor. I know because of the math here that it's just identified, which means all of the covariances between the items are perfectly reproduced by the 3 loadings. Hooray! But what are those loadings? If I get standardized loadings back that are like 0.1, 0.2, is that good? No, that would mean that it's like each of my items is, 4%, 1% factor. So even though the math holds, like the covariances are perfectly reproduced, that's a whole separate concern from whether the covariances are worth reproducing. So you can have well-fitting, perfectly fitting models that are garbage because they are perfectly reproducing the non-relationships in your items. So this goes back to the very first thing you can do is stare at a correlation matrix. Stare at just a regular old Pearson correlation matrix for your items, because that can be estimated no matter how few cases you have. If those correlations aren't there, game over. Because the rest of all of this is designed to try and reproduce those correlations. And if they're not there, there's no point. There's just not. And you would not believe how many times I have answered that question in consulting with colleagues. I have perfect fit, but none of my loadings are significant. Yes, the model has accurately described the fact that you have no relationships. Congratulations. It's not the answer they want, but that's the truth. That's what that would mean. Okay, so under-identified, you have more parameters trying to be estimated than data with which to estimate them. No. Just identified is when they're equal, means that you are just reproducing the data exactly, not testing anything. Over-identified is when you have fewer parameters estimated than you could have. Positive degrees of freedom left over. That's what we want. So I would say that given that 4 is the lowest number that allows you to test, in any study design, I would say a minimum of 5 items per factor because that gives you room for one of them to suck and still have 4 left over. If you want to hedge your bets, maybe 6 at a minimum. This says nothing about reliability though. Reliability comes from the strength of the factor loadings and the number of items. So if you want to have really good reliability, you want way more items than 6. All right. Other questions? Looks like the chat window has slowed down. We're about out of time, so that's just as well. So questions on any of this? All right. So then you have an assignment due Monday. Homework 1, it is due in icon. So under assignments, you should be able to upload your file. Please upload it in a form that's editable so I can put in comments. And please also remember to include the PDFs of the sources that you're reading. That way, if you have questions about what people are talking about in the article, I can actually open it and answer them. And as with all of the written assignments in this class, if there's any information that is missing or sufficiently unclear that I dock you points, you will get a chance to revise it to get your points back and submit that later in the semester. So that due date will be several weeks from now. All right. Any other things before we adjourn? All right, then let's call it a day. Stay safe, stay sane, have a good weekend, and I will see you guys next week. Peace out.
Lisa, I have a question.
Yes, good to see